In this video, I will be explaining you a named lemma, that is symbol approximation lemma. Okay, so here you can see the statement. Okay, and this is my notes that I have prepared to make to understand the proof of the theorems easy. I made this notes. Okay, so you can see this. So let f, you are taking a function that is small f, and they are talking about this small f. This small f is measurable function, real valued function, and this function is on the set E. Okay, now assume this f is bounded also. In addition to these, f is bounded also. Okay, then if these conditions are there, then for each epsilon greater than 0, there exist symbol functions. The symbol functions are pi epsilon and psi epsilon. Okay, they are also you are defining on E. Now on E, which have the in between there is a sentence which have the following approximation properties. They are these two. Okay, this symbol function have these properties. They are this f, you have to write this f. This in the first two sentences you are talking about this f, right? So this f lies between these two symbol functions. That is what you come to know from this inequality. And from here you will know 0 less than or equal to psi epsilon minus pi epsilon less than epsilon on E. These are the two conditions will be there if f is measurable, real valued function, and if f is bounded. If f have these properties, then there exist symbol functions. They are pi epsilon and psi epsilon, and they will have these what properties? Following approximation properties. These two properties. Okay. Now let's pass on to the proof of this lemma. Let's see, you are taking a open interval first, that is open interval c comma d, and you are saying that in the here you can find the sentence, complete sentence. Let's see, open interval c comma d be an open bounded interval that contains the image of E f of E. Okay, in this open interval you can see the image of E, and the image of E is f of E. Is that clear? And in the next line, you are considering a closed interval, that is c comma d, and you are going to partition this interval, and that is what this. This is how you are partitioning this closed interval c comma d. You have to write like this. Consider c is equal to this be a partition of closed bounded interval. This is the closed bounded interval. Okay, such that yk minus, when you find the difference between yk and yk minus 1, you are going to get the value. That value will be less than epsilon. That is how you are considering, and the k value lies between 1 and n. Okay, now you are defining some other thing also, that is you are defining ik is equal to closed open interval yk minus 1 comma yk, and ek is equal to f inverse of ik, k lies between 1 and n. Okay, the same thing that you have wrote just before. So here you are defining these two things. From this you are saying, you know that here ik is an interval. Okay, we have a proportion that every interval is measurable. So from that proportion you can say here this ik is measurable. If ik is measurable and f is also measurable, that you have in the statement, right? From the statement you come to know f is measurable, right? So here you are writing, since ik is an interval, every interval is, since ik is measurable, f is also measurable. If f is measurable, then f inverse of ik, if these two are measurable, then f inverse of ik will be also measurable. That is what you are writing. Hence, if these are measurable, then this will be also measurable. So that is how you are writing. Now you are defining two functions, that is symbol functions. You define pi epsilon and psi epsilon on E, and you are defining like this. The value of pi epsilon of x is equal to yk minus 1 and psi epsilon of x equal to yk. That is how you are defining. Now pi epsilon, the value of pi epsilon is equal to summation k is equal to 1 to n. This yk minus 1 chi of ek. Okay, and psi epsilon is equal, this is how you are defining. Okay, psi epsilon is equal to summation k is equal to 1 to n. The place of here yk minus 1, here you put yk, then chi ek. Okay, now in the next line what you are doing is you are taking that x belongs to E. Okay, you are taking a point that is x, that x belongs to the set E. Now since we know that in the second line, I think in the first line you have wrote that open bounded interval C comma D contains the image of E that is f of E, right? That sentence you have wrote in this line. You are using that sentence with this notation. You are writing it with notation, that is f of E contained in the subset of C comma D, open interval C comma D. There is a unique K comma 1 less than or equal to n, for which you are writing this yk minus 1 less than or equal to f of x less than yk. Now you know that in here you have took yk minus 1 is equal to pi epsilon of x and psi epsilon of x equal to yk, right? Here you will substitute this value here, so that you will get this, and from this you can write pi epsilon of x less than or equal to this, less than or equal to this. So from this you will get this. So first condition of approximation property, first properties of approximation that you have to prove in this lemma, you have proved. Now your intention is to prove the second approximation property, that is this. Okay, so let's see how they are proving this. Here you have to mark this as equation number 1 to get to prove the second property of approximation. What you have to do is equation, you have to subtract equation 1. Sorry, what you are doing is you are subtracting pi epsilon of x from equation number 1, so that you will get this. So from this you will get this. So this is what the second approximation property that we have to prove in this lemma, right? So finally you have proved both the properties, simple approximation properties. Okay, is that clear?